Hello. Hi. 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 Hello. Oh, no mask. That's such a revolution. I guess it's like the third day in a row. I know, but it's yes, you. Yes, you. Um,
I'm in
that,
an empty classroom, that's why.
oh, that's a good reason. Okay, that's a good. Whatever the reason is, it's good. All right, awesome. And a voice. No mask and a voice. Okay, wait. Okay, I'm gonna start seriously. Sorry, but that's very good. Okay, so yes. Hi. Well, I guess we have. Okay. So hi, Liz. I'm gonna do it this way. Okay. So hi, Liz. Oh no, I guess that's mean to Maisha. Well, it's gonna be okay. Hi, Lizzie. Hi, John. Hi, Jayla. Hi, Maisha. Okay, that was the visual. Oh, and hi, Noel. Hi, Eric. Sorry. I just did the visuals first. Okay. And now I'm doing the thing. Hi, John. Hi, Maisha. Hi, everyone. And Lizzie. Hi, Jayla. And Jayla. Hi. Okay, here's where it gets crazy. Hi, John. Hi, Eric. Excuse me. I mean, hello, Eric. Oh, wait. Oh, okay. Thank you. Direct chat. Got it. Got it. Hi, and good afternoon, Noel. Hi. Oh, now. Hi, John, CO, Lizzie. Hi. Okay. Hi, Lizzie, CO, John. Hello, John. Hi. Okay. Hi, Maisha, Lizzie. Hi, John. Okay. This is where it gets crazy. Hello, Jayla. Hi, Maisha. Hi, Noel. Hi, John. Okay. This is like an episode of The Little Rascals. Okay. But no, hello, all of y'all. With all your crazy yes. Eric is like he's like the what's the word? He's like the silent but deadly. Wait, that's weird. I don't know. Anyway, you may not know this, but he asks very, very, very good, deep, penetrating, challenging questions in formats that other people don't hear. I'm just saying that. I'm just saying it's known. Okay, but all right. So hello, everybody. I'm glad you're all here. I'm glad you're all safe. We're going to do some physics now. Oh, sorry. Did not mean to do that. I meant to do that. Okay. Yes, we're going to, well, actually, I guess that is what I meant to do. Anyway, we are going to do physics, and then we're going to have a very nice break. Well, actually, the physics that we're going to do actually is on this page here. I just want to remind, all right, so I want to talk about this stuff that's on the page right here. The two equations that are on the page right here are the equations that we began discussing on Monday. I want to discuss them more now. Remember, the rest of the semester, in a way, ultimately is about fields. I mean, the whole point of the rest of the semester, to put everything together, is ultimately about fields, specifically, particularly, most primarily about electrostatic fields. That's where we're going with all this. Now, I haven't explained yet what a field is, but fields are our topic for the rest of the semester. The way I want to get at fields, the way I want to explain them to you is by taking a step back and still making sure that we're very clear on the aspects of forces, on particularly two forces that we're using to compare and contrast kind of for the rest of this course. Okay, so what's on the page here was written down yesterday, but I want to unpack it more today. Hold on, just change the view here. Sorry. Wait, sorry. Okay. The equation at the top is the law of universal gravitation. So that's gravity on the top. The equation on the bottom, the second equation, is the law of electrostatic interaction. The top one is gravitation. The bottom one is electrostatics. The top one is Newton from the middle 18th century. The bottom one is Coulomb from the middle 19th century. Okay, they're different equations, but they're very, very similar, and it's important to see how similar they are. And it's not a coincidence that they're so similar. Okay, the one on the top tells how any 2 points of mass, any 2 bits of mass in the universe interact with each other, specifically how any two bits of mass in the universe pull on each other, right? So, and again, technically what I'm saying right now is sort of review, at least from Monday, but I want to make sure it's clear. So according to the top equation, if you have any two bits of mass 1 and mass 2, and they're separated by a distance r, mass 1 will pull on mass 2 with an amount of force, with a number of newtons that is directly proportional to the mass of one, directly proportional to the mass of the other, and inversely proportional to the square of the distance between them. Okay, that's gravitation. Gravitation is always a pull, and it's always governing over masses, and it happens automatically between any two masses anywhere or everywhere in the universe, no matter how big, no matter how small, no matter how far, no matter how close. Yes, awesome. And the distance is r. Yeah. Okay, good point. Yes, I mean the answer. So John's asking in the chat, is the distance r, and are we using r because of the word radius? Yes. I mean, in fact, okay. So good question, very good question. In some books, they'll say d instead of r. Not most books, but some books they'll say d instead of r. But traditionally, we use r. Yes, it means distance or displacement, and yes, we're using r because ultimately it refers to what we would call a radial distance or a radial displacement, partly because sometimes ultimately, especially when we're, sorry, someone's here, hold on one second, sorry. Oh, that's a really good question. Okay, wait. So again, I forget. I always forget that you guys can see the public chat. But John, so I guess I don't have to read it out loud. But John Ford's asking, does that mean we have to get arc length and angle involved soon? No. The good news is, no, we don't. Not in this class anyway. I mean, we certainly could involve them. But okay, all right, fine. So no, the answer is no, we don't. The reason the word radius. The reason we're talking about distance as though it's a radius is, first of all, a lot of times, ultimately, in the context of gravitation, a lot of times what we end up talking about are orbits. That one mass, like a planet, could be orbiting another big mass, like a sun or a star, and creating an orbit. And that's one reason we think of the distance as kind of a radius. But even when we're talking about orbits, which we a little bit will in this class, even there, at least in this context, we don't have to get involved in trigonometry as such, but fair question. Okay, good. Okay. Okay, so R stands for the distance between the two objects, between the two masses. M1 and M2 stand for the masses. Now, note with the second equation, electrostatics, exact same concept. I was trying to say this Monday. Exact same concept, and in fact, exact same mathematical structure, mathematical form. In the second equation, we're saying if you have any two bits of charge, like a proton and an electron, or two protons or two electrons, separated by a distance r, they will pull or push on each other with an amount of force, with a number of newtons that is directly determined by those quantitative pieces of information. In other words, a number of newtons that is directly proportional to the charge of one, directly proportional to the charge of the other, and inversely proportional to the square of the distance between them. Okay, and then we look in the chat. Okay, just got something in the direct chat. Okay. Oh, sorry. Okay. So, okay, good, funny point in the direct chat. But as far as the public chat, what Lizzie's saying, right? So, okay, so M stands for mass, and I think we said this Monday, but yeah, M stands for mass. Q stands for charge. So M is mass, as in measured. And stop me if I didn't do this Monday. And if I didn't, I'll start writing it down more carefully, but I think we did. But M stands for mass measured in kilograms. So M1 and M2 are just two arbitrary, let me be more specific. M1 and M2 are point masses, like they are little bits, little tiny volumes of whatever amount of kilograms we want to say, right? So we're always assuming we're talking about little dots here. We're talking about elemental pieces of whatever kind of material we're talking about. In the case of the first equation, we're talking about two masses, and we call them M1 and M2, but we generally make one a capital M and one a lowercase m, or one a big M and one a small m, just to indicate or remind us that one of these masses is probably likely bigger than the other. And we're just trying to keep them straight in our mind. So M1 would be like the big mass, M2 would be the small mass. And the Q's are charges measured in coulombs. So in fact, okay, so and charge means as in like the positive charge of a proton or the negative charge of an electron. Tell me if I've, but in fact, I'll modify that further, or I'll explain that further. Hold on a second. Okay. So again, M stands for mass, Q stands for charge. I don't know why we use Q for charge, but and also and units wise, I might put this on the next page. Remember, in units wise, mass is measured in kilograms. Charge is measured in coulombs, COULOMBS. Okay, and I'm going to go a step further now, as long as Lizzie's asking this very fair question. Okay, I'm going to go a step further and say, if we're thinking of two masses pulling on each other, a big one and a small one, like you might think of like the sun and the earth, or the earth and the moon, or the earth and some brick that's falling toward the surface of the earth or something. We'll also introduce this piece of vocabulary where from here on in, we refer to the big mass, the M1, the earth, as the source mass. And we refer to the other M, the M2, as the test mass. We think of, when in this designation, we think of M1, when we call it the source, we're thinking of it as the thing doing the pulling, exerting the pull, being the creator of gravitation, so to speak. And the other mass, the M2, as like the receiver of the pull, or what we technically call in physics the test mass, the mass that's sort of testing, receiving, experiencing assessing, measuring, but testing the strength of the pull. So we think of M1 as pulling and M2 as being pulled. Now, that's just a way of thinking. That's just a way of focusing our attention on the relationship. Like when we talk about the sun-earth system and we talk about the sun pulling the earth, we would refer to the sun as M1 and we refer to the earth as M2. Please understand, that's just like a way of focusing on it for a moment. Multiplication is commutative, and Newton's third law is true. So if M1 is pulling on M2 with a gravitational force, then necessarily M2 must also be pulling on M1 with the same magnitude of gravitational force. So if the sun is pulling on the earth, it is also at the same time and in the same way necessarily true that the earth is pulling on the sun. And when we're talking about the earth pulling on the sun, then we would refer to the earth as the source mass, and we would refer to the sun as the test mass. Okay, it's just a way, it's just a perspective thing or a way of looking at the situation. But once you've decided in your mind what's doing the pulling and what in your mind is being pulled, when you're drawing those diagrams or whatever, then we refer to the puller as the source and the pulley as the test. Okay, now the same thing can be said of charges. There's a source charge and a test charge, Q1 and Q2. That can be a proton and electron, or a proton and a proton, or an electron, whatever. Okay. But hopefully that, I don't know if that answers that. Hopefully that answers that. But now going, wait. Yeah, all right. As long as you're asking, that's a very good question. I mean, good question, Lizzie, and good question, John Ford. So yes, all four, and sometimes this can be confusing, or it's good to remind ourselves of this. All forces are necessarily symmetric interactions. But if the sun is pulling, so I'm answering John Ford's question in the chat right now. I mean, he says, so they're pulling each other with the same magnitude, but it's just enough to make the earth move, but not the sun. So here's the deal. All forces are symmetric interactions. That is the nature of Newton's third law. If the sun is pulling on the earth with a certain number of newtons, then the earth is necessarily pulling on the sun with the same number of newtons. That is definitely the case, and that has to be the case. However, that's Newton's third law. That's the character of a force. However, there's also Newton's second law, which says that net force equals mass times acceleration, right? Which means this: the sun is pulling on the earth with a certain amount. The earth is pulling back on the sun with the same amount. But the sun and the earth are two totally different masses. The sun is an enormous mass. The earth is a tiny mass comparatively. So the same force, when exerted on these two different masses, is going to have a much larger acceleration effect on the smaller mass. F net equals ma. Given the same F, m and a are inversely proportional, right? So it's a very good question, but part of the answer is, right, if the sun and the earth pull each other with the same amount, the earth is going to accelerate a lot more than the sun. Is the sun going to accelerate at all? Yeah, a little bit. The sun is affected by the earth. It's just not accelerated to nearly the same extent. So I don't know if that makes sense or not, but that's right. That's just like if I push off a wall, if I push against a wall, I go flying back. The wall doesn't. Now that's not because I'm stronger than a wall I mean, I push the wall, I go flying back, right? I push the wall, but I go flying back. Why? Because if I push a wall, it pushes me with the same exact force, but I'm a lot less massive than a wall. So I go flying. You see what I'm saying? So yeah, good point about John. And keep the questions coming. It's totally, I mean, today's a little bit discussion. We're not going to do that much math today. I want to unpack certain aspects of these forces. So feel free to keep asking these questions if you want. Okay. So notice these two forces, they're about two different things. One's about masses, one's about charges. they're both about point. I mean, they both tell you what the tiniest little bits of these kind of materials do to each other, but one's about masses, the other's about charges. But they have a couple of things in common, these two forces. First of all, they're both called fundamental, is written at the bottom of the sheet. They're both called fundamental. Why are they called fundamental? Because in order for these forces to be enacted, an object doesn't have to do anything in particular. All it has to do is exist. What I mean is, according to the force of gravity at the top, one bit of mass will automatically pull on any other and every other bit of mass automatically. As long as the two pieces of mass exist, they're going to exert gravity on each other. Neither one of them has to reach out and physically touch the other. The force happens, the force does not require physical contact or physical touching. This is unlike the force of tension, unlike the force of friction, unlike the normal force from one surface on another, right? Like the force of tension in a string, if I want a string to pull you toward me, I've got to, like, the string has to wrap around you or touch you or pull you somehow. The string doesn't exert tension on you unless it comes into physical contact with you. The string actually has to grab you to pull you. But for the sun to pull the earth, apparently, it doesn't have to reach out literally and do anything physical other than just be there. That's the sense in which we call it fundamental. Now, that's the same thing with protons and protons, or electrons and electrons, or protons and electrons. If a proton is here and an electron is here, evidently, they will just automatically be pulling on each other. So that, in other words, they exert their action at a distance. That's what it says at the bottom, right? Action. All forces are interactions. All forces are actions. Tension is an action. Normal is an action. Friction is an action. But some forces, these two, are actions at a distance, meaning a physical touch does not have to occur. Let me take this a step farther and make it even clearer. Like, the sun evidently pulls on the earth, or the earth pulls on all random objects, such as this bottle of Dr. Pepper, which you sort of can see and sort of not. If I let this bottle of Dr. Pepper go now, it's pretty evident that the center of the earth is pulling on it. It starts falling towards the center of the earth, right? Now, I mean, whether you're used to that idea or you find that idea mysterious, that idea seems to be true, that the earth automatically pulls on this bottle. It doesn't have to touch it in order for it to seemingly grab it and yank the bottle toward the center of the earth. Even when there's nothing in between, or especially if there's nothing in between, the bottle tends to fall. Now, so apparently the force of gravity can happen through empty space. Similarly, the attraction of a proton and an electron can apparently happen through empty space. Yet, on the other hand, or similar, yet at the same time, if I put a table in between the center of the earth and this bottle, you can't see, but if I put this bottle on a table, and so now there's a table blocking the bottle from falling. Let's be clear, by putting a table underneath the bottle, I don't turn off the force of gravity, right? When you put a table under a bottle, when you support an object, you don't make gravity disappear. You don't fight gravity. You just counterbalance gravity. Put another way, if we drew the free body diagram of the bottle, there'd be an arrow down toward the center of the earth, which we would designate mg, or weight, or FGR, or whatever. We'd have an arrow down for the gravitational pull on that bottle. And if it were on the table, we'd have an arrow up designating the normal force exerted by the table, right? In other words, when we put a bottle on a table, we don't get rid of gravity. We just introduce another force in a different direction, which adds to the force of gravity with a minus sign, and ends up making the net force, the total amount of force on the bottle, become zero. That's a very important distinction. Again, what I'm saying is when you put a table underneath a bottle, you don't get rid of gravity, you just add a countervening effect to gravity. In other words, gravity, the pull from the center of the earth, seems to occur through empty space and just as easily through desks. Oh, and by the way, what's my evidence for that? What's my evidence for the fact that when I put a table underneath the bottle, I don't make gravity disappear. I simply shove up on the underneath the bottle. Well, my evidence is this. When I put a bottle on a table, the table doesn't shove the bottle up and make the bottle fly up into the air, right? The table's clearly pushing up on the bottle, but if the table were the only game in town, if only the table were pushing up on the bottle, it would accelerate up, but it doesn't. It just sits there. In other words, the upward force of the table is balancing or being balanced by the downward pull of the center of the earth. They're both still there. Right now, I mean, that may be totally obvious to all of you, but what I'm trying to emphasize when I say that is notice that gravity seems to be able to act just as easily through empty space as it does through matter. It doesn't seem to care. It doesn't require a touch to work. Gravity, the earth doesn't require touching objects in order to pull them, but it's also not bothered if you put any touchable objects in between the earth and gravity. That's how fundamental it is. You see what I'm saying? Gravity is just a pull, an interaction that just seems to just occur and exist and act between any two objects, any two masses that you can think of anywhere in the universe. It just happens. It's fundamental. Same thing as electrostatics. Any proton, any electron, super close, super far, they automatically pull on each other through empty space or just as easily through matter, just by virtue of existing. So the gravitational force is fundamental. The electrostatic force is fundamental. Forces like friction or tension or the normal force, they're not fundamental. I'm not saying they're not real. I'm not saying we don't use them in physics all the time, but they're not fundamental in this way. They don't arise just by virtue of certain types of objects existing. Okay, so we've got two fundamental forces in this class so far: the gravitational force and the electrostatic force. Both fundamental, both actions at a distance, both inverse R squared form. I mean, they both are inversely proportional to the square of the distance between the objects. I'm just saying, note that the two forces that seem to be fundamental, both seem qualitatively fundamental, both seem to be mathematically inverse R squared. I don't know why yet. I'm just saying that's an interesting observation, and it's definitely not a coincidence. In fact, the Coulomb force that governs between charges, which was developed in the 19th century, Coulomb was very, very aware of the Newton gravitational force. It's not a coincidence at all that he conjectured and then verified and posited that the fundamental interaction between bits of charge would act mathematically, just like the fundamental interaction between bits of mass. So that's what we have so far, is that we've got these fundamental interactions that happen through empty space and have an inverse R squared character. Okay, that's what we have so far. Now, I want you to know that that these things are true, but they're not self-evident. It's not obvious that the world should work this way. In fact, I'm not even arguing that the world should work this way. I'm just arguing that the world appears to, in fact, work this way. When Newton developed or began to develop the top equation, the universal law, the law of universal gravitation, he was critiqued by certain people for this idea. Let me back up and say that Newton, who is mentor to many of us, those of us who like physics and do physics, of course, owe a great debt to Newton and to Galileo and so forth. And in many ways, we consider Newton, our grand teacher. or grand mentor. Well, Newton himself had mentors. One of Newton's mentors was a man that you don't hear about frequently in school, but a man named Richard Bentley. Richard Bentley was a don at Cambridge University. I mean, in other words, he was a professor in a sense, a residential professor, and a very esteemed one. And Newton and others, pardon me for a second. It's all that. Oh.
I only saw switch
So
and your switch.
Hold on, I am teaching. If it wasn't packed, then I don't. It should have been. Did you look
Show
at
me.
I'm teaching right now, but if it wasn't packed, then I apologize. Hello, good to see you. Hold on, too. Did you bring it in the car this morning?
No.
Then I don't know. I'll text mom and ask her to bring it. Okay, mom's coming, so I'll ask her to bring it. Wait, is it there? Is it there? Is it there or no? Wait, yes or no? Wait, yeah, okay, okay, no problem, okay, okay. Sorry, hold on a second. Totally, that was rattling. That's funny. Wait, how do you know about the Beyblade? Oh, right. Oh, yeah. I totally did. Actually, he was very nice, but I did bring him that, and that was a big hit. Actually, thank you. Okay, sorry, but yes, he's got that. I was good for thinking for a minute. How did you know about that? Okay. Sorry. He's so spoiled. Okay. So Newton. Oh. Yeah, I know. I believe it. You probably would. I know. That's funny. And I'll tell him that someday when he can appreciate it. You're saying you don't learn effectively. Wow. Oh my God. Oh my God. Oh no, he didn't. Wow. That will. Oh my God. Okay. This class is so funny. All right. I feel like I'm being. Okay. Can you tell I'm a little tired here? Okay. Okay. Newton had here report. Okay, how about I report the bully to the Pokemon champion? We'll see what happens there. I mean, I'm going straight to the highest authority I know. Okay, yes, I will right after class. And talk about bullying. Did you see how my 7-year-old just bullied me? I mean, that was bullying. I mean, I don't know my switch line. Okay, but okay, very funny. Oh my God, I think the dean. Okay. So Newton had a teacher that you don't hear about much in class. You should trust his authority. All right. I'm turning off the chat because I can't. I mean, I'm turning off the. Newton had a mentor named Richard Bentley. I'm not expecting that most of us have heard of Richard Bentley, but Richard Bentley was very important to Newton. And to Newton's contemporaries. And at the time that Newton was in pre-publication of this gravitational theory above the equation, a scientist of the day, of the mid-18th century, wrote a letter to Richard Bentley criticizing Newton's theory of gravitation, criticizing in particular this idea of action at a distance. You see, again, nobody had mathematically formalized this prior to Newton. We, in some sense, observe it all the time, and we observe things falling to the earth all the time. We understand that there's something that we might call gravity happening all the time. But what hadn't happened before Newton, first of all, the idea of things falling to the surface of the earth being linked formally, scientifically, prescriptively, descriptively to things everywhere in the universe falling. The idea that whatever it was that Earth was doing to objects near it was the same thing that the sun was doing to the Earth, or that the Earth was doing to the moon, or that Jupiter was doing to Jupiter's moons. That idea had not been formalized prior to Newton. The idea that it was all one common force among all objects, not just earthly objects, but also it certainly hadn't been mathematically nailed down in one equation like this. This, again, please understand this equation is meant to be universal. Supposedly, and to this day, we still essentially believe any two bits of mass you pick, any two bits of mass you pick, whether it's 2 bits of mass on Earth, or a bit of mass on Earth and a bit of mass on Jupiter, or 2 bits of mass on Jupiter, any 2 bits of mass anywhere in the universe you pick supposedly automatically pull on each other through empty space with a specific number of newtons dictated by this precise equation. Now, that had not happened before Newton. This is a big, bold idea. And Newton was criticized for this idea in a letter that a scientist of the day, of the 18th century, wrote to Richard Bentley. And in this letter that was written to Richard Bentley, this letter which survived, of which we have excerpts to this day, the letter is pretty scathing. Okay, it makes a pretty direct attack on the sense or the plausibility of this notion of gravity. And it's such an important critique. Now, again, I'm not saying that gravity is wrong. I'm actually here to say that I think gravity, the idea is right. But it is a fairly bold idea and a pretty wild idea. And I think it's worth, before we go, for a number of reasons, before we go any further, I think it's worth looking at this idea of action at a distance as it applies to gravity and ultimately then as it applies to electrostatics. I want to show you this criticism that was written about Newton to Richard Bentley. This criticism that I'm going to show you was written by a scientist of the day that you do actually know, that you are familiar with. And I did put this letter in the Google Classroom, like it's in your file now. I put it in, like an hour before class, but I'm going to temporarily put it up on this so you have it. But I'm going to put it on the screen for a moment. I'm going to switch screens just so you, so we can make a point here. Hold on. Oh, wait, sorry. Okay. So this is what I'm talking. So again, this is in your, if you want to refer to this later or whatever, this is in your Google Classroom. I'm just trying to move my screen. This is in your Google Classroom. But all right, so this is an excerpt from a letter that was written in the mid-18th century by a historical figure that you actually do know. We'll talk about who it is in a moment. And I'm going to turn this off too. Hold on a second. Pardon me. And in the letter and this letter is written to, it's not written by, but it's written to Newton's mentor, Richard Bentley. And it says here, okay, so hopefully you can see it on your screen. It says, and this is regarding the idea of action at a distance, regarding the idea that one mass could pull on another mass through empty space without touching. So it says, it is inconceivable that inanimate, brute matter should, without mediation of something else which is not matter, operate on and affect other matter without mutual contact, right? So far that says, I mean, hopefully you understand. Oh, something in the chat. This might be worth it. Yeah, okay, right. This is seriously, right. Talk about OG. This is some serious OG. I'm glad you, and feel free to make the joke. Any evidence that you can give me that you're understanding how intense this language is. Yeah, this is intense. I mean, so far, just that first paragraph, he's saying it's inconceivable, like incomprehensible, right? Like you can't even imagine it. That inanimate brute matter, so that just like physical objects, like just bits of mass, could, without anything else material in between, operate on and affect other bits of material without touching, right? So it's now, and again, gravity is saying that that's what's happening. This guy is saying it's inconceivable that we should believe that. I'm looking at the chat. Right. Okay, that's funny. But yeah, I mean, joking. I mean, this is some serious, and also don't forget, I mean, right, this is 18th century. So for the 18th, they were all obviously very polite and sophisticated then. So this is very gangsta language for 18th century. I mean, my God, if this is the equivalent of a subreddit, like, whoa. And it goes on. that gravity should be innate, inherent, and essential to matter so that one body may act upon another at a distance through a vacuum without the mediation of anything else by and through which their action may be conveyed from one to another, is to, now check this out, seriously, look at this, is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. Now, I mean, and I know it says no man, I should say no person. I mean, of course, the person writing this was probably only thinking about men, but he's literally saying, he's saying no, but, and when they say a competent faculty of thinking, they don't mean like university faculty. They're not saying anybody who has good professors. Competent faculty of thinking, they're just saying like reasonable facility or capacity or ability to think, right? So they're saying, literally, they're saying at the bottom of the page here, is so great an absurdity, is so ridiculously absurd that no one who even has a clue, a remote clue, should ever fall into thinking about this, right? That's what it's saying. It's basically saying that like only an idiot would believe such an idea as this. And what is the this? The this is the idea, Newton's idea, that one object would be able to pull another object automatically through empty space without touching it. The idea that the sun should be able to pull the earth to it through empty space without touching it, or that the earth should pull on a brick to it without touching it, or ultimately, if we go a century later, and then I'm going to look at the chat, by extension, according to this, then the idea that a proton should pull an electron toward it, or that a proton should repel another proton away from it through empty space without touching it, is a totally absurd idea, is what this guy is saying. And this guy, remember, is writing to Newton's mentor. It's basically like someone ratting on you to your teacher, like, can you believe this guy? Like, I want to get him in trouble. Send him to the back of the class. Now, hold on. I have more to say about this, but let me check out the chat. I'm glad you're putting something in chat. Lord knows what you're putting. Yeah. Oh, no, right. Facts. Facts. Wait. Yeah, no, and for real. And I'm glad John and Maisha are getting in on this. And even if they're like, you know, half joking, half not, they are totally right. John and Maisha are like, this letter is basically saying like, yeah, the big advancement or the big theory, the big accomplishment of Newton's life is preposterous, is stupid. Right. That is what they're saying. Now I'm going to go further. And I'm not trying. I am a little bit trying to be dramatic here with all of you, but I'm not making this up. I mean, this is real. And I'm not doing this to trick you. Like, I'm not saying this, I'm not bringing this up to say, so gravity is stupid. I don't think gravity is stupid, but I do want you to appreciate what's really weird about, like, the rest of this class is about action at a distance. It is. It is about masses being able to pull on each other through empty space. It's about protons and electrons pulling on each other through empty space, or electrons and electrons pushing on each other through empty space. So before we go do anything more in the class, or before we take a break, I want to pause for a minute and tell you what a revolutionary or sort of, you know, tricky idea this is. Now, why this guy is saying that it's totally absurd, it's not like Newton is the first person ever to notice that things fall, okay? And frankly, it's not like Newton's the first person ever to notice that some things seem to sort of act at a distance. I mean, we've all played with magnets. Like, what we're basically saying here, what Newton's saying is that all bits of mass kind of act like little magnets, or that all protons and electrons sort of automatically act like little magnets. And we've all seen magnets, like, we haven't talked about them yet in physics class, but we've all seen that you could take a hunk of iron near a paper clip, and then the paper clip, like, you know, or like you could take a hunk of iron like near your tabletop, and you could have a bunch of paper clips on the tabletop, and they start moving around the tabletop, even though nothing's touching them. Right, we've seen that, but let's note a couple of things about that. Number one, when we were first seeing it as kids, we thought it was very cool, or at least I did. I liked playing with, and not just because like I'm a science nerd or whatever, but like I think most kids find magnets, especially when you could do little tricks with magnets and get things to happen that look like magic. There's a reason it seems magical. It literally does seem magical because something is affecting something else without touching it. That's almost is the essence of magic. Now we get used to it after a while. So after a while, it doesn't seem that unusual because it is usual. That doesn't mean though that it isn't fascinating. Number one. Number two, now I want to be much more specific. Why is Newton being attacked for this idea? Like, again, if Newton's not the first person to ever notice something falling, or if Newton's not the first person ever to play with a magnet, why is Newton getting attacked here? Well, because Newton put math to it, in part. And by putting a math equation to this, he's now saying something even more specific and perhaps more hard to understand and more crazy. I want to break this down for a moment for all of you. In fact, I'm going to stop this. Well, no, I'll leave the screen up for a second. Think about the fact that there's an equation. The equation is saying that one mass, like the sun, pulls on another mass, like the earth, with an amount of force that is specific, precise, numerical, measurable, reproducible, and that specific, precise, numerical force is totally determined by how heavy the earth is and how far away it is from the sun. Okay, like that's what the equation's saying. Now, if that equation is true, let's follow this through for a minute. I mean, like, let's play this out in your mind with me, if you don't mind, for a minute. According to the equation, F equals gmm over r squared. That means the sun exerts a pull on the earth that's a certain number of newtons. So it pulls the earth toward it. Then according to Newton's second law, if nothing else is going on, if nothing else is happening in the universe, whatever, the earth starts coming a little bit toward the sun, right? Or if you don't like that example, or if that example is too abstract, think of just a brick or something falling toward the earth. The center of the earth pulls on the brick with a number of newtons, an amount of force that we call weight, a number of newtons that is totally determined by how heavy that brick is and how far away it is from the center of the earth. So the center of the earth starts pulling on the brick, it exerts a force, the brick starts accelerating toward the earth, it starts falling towards the earth. So now a little time passes and the brick is a little bit closer to the earth. Now think about this really carefully and honestly. I'm not asking you to do any math in your head. I'm just asking you to consider what the math has to mean. If the math is right, if there's any equation at all, if it's true that the force exerted by the earth depends on how massive that brick is and how far away that brick is from the earth, then that means as the brick starts falling, as the brick gets closer to the earth, according to that equation, the R must change. I'm not asking you to do the numbers, just follow the logic. If the brick starts falling toward the earth due to the gravitational force, then the R has to get smaller. And accordingly, the earth now has to pull on the brick more strongly, more intensely, with a greater force. Well, wait a minute. The brick gets closer to the earth and the earth adjusts its pull and pulls harder now? Wait, how does that happen? If the brick gets closer to the earth and then the earth starts pulling harder, doesn't that have to mean that the earth got the new information about the brick's new whereabouts in the amount of time that the brick fell? Like, in other words, if the strength of the pull being exerted by the earth actually depends on how far away the brick is, then doesn't that mean that when the brick gets closer, the earth somehow must learn this because the earth starts pulling harder, right? Now, I'm not saying the earth is like human. I'm not saying it has to know it in a conscious way. I'm not trying to be ridiculous, but I'm saying if we're believing scientifically, physically, that the earth grabs the brick, or not, if you don't like the word grab, whatever, like yanks, tugs, draws, attracts the brick with an amount that depends on where the brick is, doesn't that have to mean that the earth has to be in possession in some inanimate but very real way? Doesn't the earth have to be in possession of this location of the brick? The brick is somewhere else in empty space, but the earth adjusts its pull every time the brick moves through empty space. So the earth has to be getting updates as to the location of the brick if this equation is true, right? I mean, really, if this equation is true, that means that as the earth reaches out and pulls down on a brick, and as a brick does the very simple, common, everyday thing of falling towards the earth, as it's falling, it is getting closer and closer to the earth. As it is getting closer and closer to the earth, the R is getting bigger, the F exerted by the earth has to be, the R is getting smaller, so the F exerted by the earth has to be getting bigger. The earth has to continuously update its pull in order to correspond to or incorporate the updated distance that separates the earth from this brick. So somehow over that intervening distance, over that empty space, the brick has to be sending the earth in updated information about its updated whereabouts, like truly, literally, not consciously, not anthropomorphically. I'm not trying to be silly, but I am trying to be dramatic, because something very dramatic must be happening. If this equation is true, it has to mean that the information of what's going on at one point in space must somehow be transmitted, conveyed to other points in space in order for these two different points in space to be interacting with each other in a way that depends on that information. The information must be traveling back and forth. That's what is initially crazy about this idea of action at a distance. Action at a distance must mean that information is traveling through empty space between interacting objects. That right there is part of what the person who's writing this letter has a very legitimate complaint or concern about. I hope you sort of understand what I'm saying. Let me just take a look at the chat and see if you do. I'm a little worried that what's in the chat is like random jokes, but we'll see. Oh. Wow. Okay. Wow. A kind of a dream come true for this class. I have to say the two things, or maybe the three. Oh, that's funny. Okay. So there's three things in the chat, and granted, two of them are jokes, but number one, they actually are very funny jokes. I totally have to admit they are very funny. But two, one of them is serious. Okay, so you see what's in the chat, right? You can all see. One thing that's in the chat is not a joke. It says, is there a wave? Excellent question. Definitely shows that at least that person is totally paying attention to what I'm saying. But then the two jokes, even though they're jokes, they also are totally showing that those people, same people, are paying attention to what I'm saying. Like, you couldn't even make those jokes unless you follow the absurdity of what I'm saying. And I'm even going to go a step further. I'm going to dare to suggest, I think those jokes are the kind of jokes you make. Remember the word that's being used here. The guy actually called Newton's theory absurd. Absurd means like wacky. It means like nonsensical, almost in a funny way, right? You almost have to make jokes. If you actually get what's so weird about this idea, you almost have to make jokes about it, partly because it is a funny idea, but also because honestly, I'm going to go out on a limb here. If you really think about this idea very seriously and try not to make jokes about it, if you really think about what I'm saying, it's actually a little disturbing. It actually almost makes us want to pursue a little relief and a little bit of humor, because it's actually a little bit of a headache to the mind to actually consider how the heck this could be. I totally do appreciate these jokes. And again, I don't think you could make these jokes unless you were understanding what I'm saying. I'm going to go a step further too. Like, look, if you're following me, and I think you are, I certainly think, at least three people are. If you're following me, and you're following me means following two things. Means number one, following the basic claim I'm basically saying that Newton is basically saying, which is F equals GMM over R squared. I'm saying basically bit of mass over here, bit of mass over there, separated by a distance R, they will pull on each other with a specific amount that is specifically determined by how far apart they are and how big each one of them is. So therefore, So I'm saying that's F equals GMM over R squared. Or if you're talking about protons and electrons, that is F equals KQQ over R squared. But then the critique that I'm raising here, that somebody whom you know actually wrote to Newton's mentor, the critique is, whoa, you're saying that a bit of mass over here can pull a bit of mass over here through empty space. Now, it's one thing that we see that sort of vaguely qualitatively happening all the time. Like we see that things fall. Yes. We see that magnets work. Yes. But now you're saying that it's like really specific and numerical. You're saying that literally you could measure the number of newtons that one thing pulls on another, and the newtons would be determined exactly by how big each thing is and how far apart they are. So you're saying that the two things that are far apart from each other, and by the way, notice there's no limit on how big the R in the denominator could be. We're saying it affects, a bit of mass in Alaska and another bit of mass in China, but similarly, a bit of mass in Alaska and a bit of mass in the Andromeda galaxy. We're saying there's no limit. I mean, the farther apart two things are, the smaller the force, but there's still a force. And we're saying, here's the critique again, and the jokes, what the jokes are about. We're saying that no matter how far apart you are from something else, way at some distance in empty space, that somehow you as a physical, brute, inanimate object somehow have the facts. You have the facts of how heavy that thing is very far away, and you have the facts of how far away it is, right? Because that's how hard you're pulling on it. If it were a brick that was near the surface of the earth, and then like a pigeon pooped on the brick, and the brick now had some poop on it, like pardon the imagery, then the brick would be heavier, and supposedly the earth would be in possession of that information and start pulling on the brick harder. That's what we're saying here. And the critique is saying that's preposterous. How could the earth possibly know how much heavier the brick just got just because a pigeon pooped on it? Or if the brick starts getting closer to the earth, how could the earth possibly know that the brick just got closer to it? Unless the brick is somehow sending the information to the earth. And that now raises two things. It then Good, Jayla. Oh, wait, hold on a second. Oh, and good question. I want to get back to two things that John said. Was it that other guy? I'm going to get back to that in a second. Great guess. I'm going to get to that in a second. But first, before I get back to the two things that John said, the force put into an object, this is Jayla's thing. The force put into an object is the force received from. Yes, that's Newton's third law. Yeah, definitely yes. If I pull on you, if I'm the sun and you're the earth, and I pull on you, you pull on me with the exact same amount of force. Yes. So somehow, that's definitely true, Jayla. Yes. So good. But now we're saying that force, whatever it is, depends on how big each one of us is. And that you could sort of understand, sure. Like if I have a fishing line attached to a fish, you could sort of imagine that the fishing line might pull on the fish with an amount that sort of depends on how big the fish is, maybe, because the fishing line's touching the fish. You could maybe imagine that. But now we're saying that even objects that are separated, that are at two totally different points in empty space, somehow interact with each other in a manner that is dependent on their vital stats. And again, I want to get back to two things that John's saying in the chat, but let me just try to say this. This is a super important thing. And again, even if we don't get much past this today, it's totally worth considering. In my judgment, I just forgot. When I say vital stats, if we believe this equation, and I am saying that ultimately we do believe it, but if we believe, I'm not going to trick you, but if we are believing F equals GMM over R squared, and if we are believing F equals KQQ over R squared, we are literally believing at some sense that what's happening over here in space, what is there, how big of an object is over there and where it is somehow, that information is somehow accessible to things happening over here in space. We're saying that somehow information is getting from one point in space to another point in space, which raises a very interesting question that John raised in the chat. John said, about 5 minutes ago, John said, is it traveling like a wave? Now that's a perfect question to ask in this class, especially at this point. Like, is this perhaps why we've been spending all this time building up this idea of waves traveling through space? It's a very, very reasonable thing to ask, a very wise thing to ask. Are we saying, if Newton is saying that M1 over here knows how heavy and how far away M2 is over here, are we saying that perhaps the information of M1 and M2 is traveling back and forth between M1 and 2 as a wave? Maybe, but here's why I say maybe. Here, and maybe even the guy that wrote this letter even maybe considered that. But there's two issues if it's traveling as a wave. Number one, if it's traveling as a wave, everything we've said about waves so far say that waves actually do travel. They actually, like sound waves, they don't just appear at your ear from the minute I talk, they travel from my mouth to your ear. That is, they follow all the normal patterns and principles of physics. They take time to get from my mouth to your ear. That's what the sound waves literally travel. They literally take time to traverse space. So on the one hand, so that raises the question, if Newton believes that the information of one mass, of its size, of its magnitude and its location is somehow getting to the other mass, is it traveling like a wave? Is it taking time? That's a really important question. There's only two possible answers to that question, yes or no, right? I mean, either it is taking time or it's not. Here's the thing. If it's not taking time, that's really weird. I mean, first of all, waves, if it's a wave, waves do take time. But if it's not taking time, that's really weird, because if the information of the sun can reach the Earth in no time, regardless of how far apart they are, then that means it's taking no time, regardless of how far apart they are. In other words, if it doesn't take any time to travel the intervening distance, then that means that the intervening distance doesn't matter, that it won't take any longer for information to go from the sun to the Earth than it would, or it won't take any shorter for information to go from the sun to the Earth than it would for the information to go from the sun to Pluto, or from the sun to some other star in some other galaxy. In other words, if it doesn't take any time, then that means that information of all objects is always getting everywhere in the universe all at once. That means the whole universe is communicating with the whole universe always, all at once. That means nothing takes any time at all. That's weird. I'm not saying that's true or false. I'm just saying, oh my God, if that's true, that's really weird. On the other hand, if it's not true, if it does take time, if, as John's suggesting, if somehow the information gets from the sun to the Earth in the manner of some kind of wave and takes time, well, number one, there's two problems with that. Number one, if it takes time, that means there's a delay, right? That means that every time the Earth gets a little bit closer to the sun, that means the Earth gets pulled by the sun, it comes in a little bit, and now the new location of the Earth has to get sent to the sun before the sun will create its new updated pull. So before the sun pulls next, it waits for this new signal or something, and the signal has to take time before it gets to the sun. So there's a delay before the sun makes the next pull. And then it gets there and the sun makes its next pull. So then the Earth comes in a little bit more, but then there's another delay. In other words, if it is traveling as waves, that means there's some kind of delay happening all the time. That means even the simplest motion, just of a brick falling to the surface of the Earth, something that seems like a continuous just stream of whoop, is actually some sort of, like on a microscopic level, is actually some sort of strobe light, kind of like, dance rave effect of like, I mean, is that what that means? That's really weird. And also, furthermore, if it does travel as a wave, which is a great thing to say, again, like honestly, it definitely shows paying attention to this class. But if the information of the Earth is traveling to the sun in the manner of a wave. Remember everything we've said in this class about what a wave is. A wave is a wiggle. A wave is a very, very complicated, intricate set of oscillations being performed by a bunch of intervening particles known as the medium, right? In other words, sound is a wave, but in order for there to be a sound wave, there must be air or water or nylon between my mouth and your ears. There is no sound in outer space, right? Because in order for there to be these sound ripples, these sound wiggles, something, for example, a whole bunch of air molecules must be rippling, must be wiggling. So if the information, if gravitational information or electrostatic information is traveling as a wiggle, which is a very good thought, and I'm not saying it's wrong, it still raises the question, what the heck is wiggling? Especially if we believe that universal gravitation literally happens universally, if we believe that the sun is, if we don't just believe it's happening on Earth where there's an atmosphere and there's air and all this kind of stuff, we believe that if we believe this supposedly universal equation, F equals GMM over R squared, if we believe that it applies to everywhere in outer space, then that means we believe it applies to space. And it doesn't seem as though there's anything in space to be wiggling or oscillating or creating these waves. So what I'm saying, what, oh wait, no, okay. What I'm saying in a long, long way, I'm trying to say that the guy writing this letter has a very, very good grounds to object to Newton's universal law of gravitation. The idea that action at a distance is mathematically describable, that it's quantitative on a universal level, that literally we're saying the amount that I pull or push you through empty space is determined by how much space there is between us and how big each one of us is a crazy idea no matter how you slice it. Either whether the information is traveling as waves or something else, whether it's taking time or not taking time, it doesn't seem to add up to anything that we can get our mind around. Doesn't mean it's wrong. I'm just saying, oh. Yeah, I'm looking at the chat. Yeah, I mean, when a brick falls to Earth, if this equation is right, that means that every moment that the brick gets infinitesimally closer to the Earth, supposedly, the status update must be sent. So I'm not sure when you say 2 minutes, I mean, it's more than every 2 minutes. It's like every moment these status updates must be being sent. And if they are taking more than a moment to get there, then what does that say for the whole process? And if they're taking less than a moment to get there, what does that say for the whole universe? Like I'm saying one of the reasons of all time to make jokes about this is that if you actually think about this too seriously for too long, it really does give you a headache. It really is crazy making. Okay. So I don't know if you, so what I want to, now we only have 8 minutes. Yeah, we have 8 minutes. What I know this is a very kind of open-ended type of discussion in a way, or I mean, it sounds like I'm just like babbling. Well, I am just babbling, but so far we have this idea of gravity with an equation. We have an idea. Oh. Well, yeah, right. It is like that, except for it does care. But yeah, I mean, supposedly, according to this, even if you're 2,000 light years away, you do care. You care because you're now going to pull harder or less hard, depending on how far away the thing is. So what we have so far is we have this equation, F equals GMM over R squared, which supposedly happens at a distance through empty space. We have this other equation, F equals KQQ over R squared through a distance, empty space. We have this guy that writes a letter to Newton's mentor saying, whoa, this Newton idea, I mean, it crazy, totally crazy. So crazy that you have to be an idiot to believe it. And this guy that writes this letter to Newton's mentor, this guy is, in fact, a noted scientist of the day. He's no slouch either, the guy that writes this letter. I think you understand what I'm saying so far. What I want to ask you is, we have 7 minutes left. Does anybody know or can get, you've heard, I guarantee you've, sorry. So you've heard of the guy that wrote this letter. And John gave a very good conjecture as to who might have written this letter. He said that the guy, oh, that's another great. All right, I have to totally admit, first of all, I do think the jokes are funny, but as far as the non-jokes, you're totally outdoing yourself. Wait, I'm just looking, where did it go? Where did it go? The two guesses or the two conjectures that John's put in the chat are really, really enlightened. They are really smart. The two, he wrote Leibniz, which many of you know was the other sort of inventor or discoverer of the calculus. You know, Leibniz worked in Germany while Newton worked in England, and they both independently came up with the calculus. They're definitely historical contemporaries. So that's a very, very good thought. I mean, it's very wise. Oh no, he didn't make it with Newton. No, in fact, to this day, he made it independently of Newton. That's what's sort of an interesting thing. They both independently came. Oh, wait, yeah. No, you're right. Okay, Leibniz did make calculus at the same time as Newton. That's correct. Not like with him, but yes, at the same time. That's totally correct. Which is why that's a very, very good guess. It happens not to be the case, but it's a very good guess. And the other person I think John guessed or conjectured, I think he said Hooke, or who did he say? He said another very reasonable. I can't remember. Oh, you just had Leibniz. Okay, wait, and sign up and good, and thank you. Totally shows you're paying attention. Lizzie, yeah, they did, yes. I mean, but first of all, they actually spoke different languages, but not only that, Leibniz and Newton actually used very different notations. And they did call it different things, but not only that, when we say that they both invented it, I mean, on paper, it looks very different. Like all the dy dx stuff that you do is like one of them, but then like the F prime stuff that you do is the other. Like they both wrote it out very differently, but conceptually it's remarkably similar. I think you heard it again. That's funny, but I really have 4 minutes, so I want to just get to this. So Leibniz is a very good guess, but it's not the case. Hooke, which I thought someone had said, would be a very good guess too, because Hooke was, as in Hooke's law, was also a contemporary of Newton's and in fact, a rival of Newton's. In fact, they disagreed very fundamentally on some very fundamental things. So that also would be a good guess, but it's also not true. Here, you want to talk about thinky hurdy or hurdy thinky. Since we only have 4 minutes left, I'm going to tell you, unless anybody else, does anybody else, I guarantee you've heard of the guy who did write this objection, this scathing critique. And again, remember, this is like, I think this is like subreddit-esque in its scathingness. I mean, literally the guy saying it's so great an absurdity that any man who is in philosophical matters a competent faculty could ever fall into it. I mean, you don't get more direct than that for the 18th century for a published letter. So does anybody else want to quickly guess? We have 3 minutes left. Who might have written this letter critiquing Newton? Okay, going once, going. Okay, so okay, just raise your hand though, since we have 2 minutes left. Raise your hand, please, or your emoticon, whatever, just to make sure. Are we all still paying attention? Like you're still with me. You still hear what I'm saying, right? I just want to make sure you hear this punchline. That's a yes. Thank you, Eric. Oh, thank you, Eric. Okay, and that's a yes, Jayla. Thank you, Jayla. Okay, is everybody else is still with me? I'm just with the 2 minutes left, the 3 minutes left. Is anybody else with me? So Eric and Jayla, thank you. Is that it? Just Eric and Jayla are the only people left? And Lizzie, thank you. Okay. And obviously John and May should cut out long ago. Oh, Stephanie, thank you. Okay. Okay. So here's the deal. Again, remember on the screen right now is this scathing critique of Newton's idea of action at a distance. And it's a scathing critique that's written in a personal letter to Newton's mentor, Richard Bentley. Okay. Oh yeah, the units are Newton. Oh, well, good point. So therefore, I'm not sure. So Jayla might be onto something here, because here's the deal. Since we only have 2 minutes, I'm going to tell you the person that wrote this letter, and I'm not trying to trick you. I am trying to be dramatic, but I'm not trying to mess with you or trick you. And we're not going to take back the equation. The equation's still true and right, and we're going to use it. But the person that wrote this letter critiquing Newton's idea of action at a distance, the person that wrote the letter is Newton. Okay, Newton wrote this letter to Richard Bentley, and he wasn't joking. he hated the theory. He couldn't understand it at all, but it was his. And it's one of his most important discoveries ever. And he hated it. And this is real. This is real. This is the fine line between genius and craziness. And in fact, Newton did. Yeah, no, yes. So Jayla was really onto something when she said that a second ago. Absolutely. Newton went to his grave being driven crazy by how much he couldn't stand. He could not accept his own idea. He thought it was absurd, yet he thought it was right. This is the essence of scientific humility and lack of bias. This is the beginning of true scientific method. This is Newton saying, I don't get this. I don't think this is the way the world should work. I don't understand how this could be. I don't understand why this could be. This violates every predisposition and pre-notion that I have of how things should make sense in the world. But this appears to be true. He's saying the data suggests this. This equation works. It makes predictions. It predicts orbits, eclipses, free falls. And by the way, and I know it's 4:20, I'm about to end, but just to be clear too, by the way, that equation, GMM over R squared, it put men on the moon in 1969. I'm not exaggerating. That equation was used. We believe in that equation so strongly that it allowed us to build rocket ships that went to the moon. It works. And Newton in the 18th century knew that it worked. So he published it as science. But then he said, I don't get it. I don't understand it. It doesn't make any sense. There's so much about the world that I do not understand, and I leave to future generations. He literally wrote, I leave it to future generations to make sense of this. How or why this could be, I do not accept. And he went crazy over it. But the data said it, and it made predictions that worked. So that's when Newton said, I'm not a philosopher, and I'm not a rabbi, and I'm not a philosopher. I'm a scientist. This seems to work. There it is. I don't know what to tell you. That is, to me, the essence of scientific humility. And it's true. And it's why we're going to use the equation when we get back from break, and why we're going to believe in fields and use fields when we get back from break. But let me just look in the chat. Right. Well, okay. Yes, but don't second guess yourself. But do, but don't, but do, but don't. Don't second guess yourself. Wait, I'm a second. I don't know what to say. But yes, no, but that's the story. Okay, so have a great break. Thank you for paying so much attention. Thank you for appreciating the paradoxes of science. And I will see you in a week and hopefully have your midterms. And I will miss you. Bye. Yes, have a good break, you too. Thank you, guys. Yes, you too. Have a great break. Yes, everybody.
Hi, Professor. Have a great spring break.
You too. Have a great break and a great break. Yes, thank you.
Professor,
Yes.
could you tell me how can I get in the fields?
Wait, how do you?
It's on